Hello, welcome. In this lecture, we are going to study systems of linear equations, and in particular, we're going to make the equations in a given system a little simpler. And by manipulating these equations, we will be able to find solutions solutions are values that satisfy all the equations simultaneously, and we'll be able to find these solutions by applying simple operations. In general, a system of equations is going to have multiple variables, and here the variables are going to be denoted with the letter x, and we're using these indices. And so in general, we're going to assume that we have n variables. So there are n of these variables, and each equation is given in this form. These numbers a11, a12 are so-called coefficients. They are known values. Here we assume that all those values denoted here with the letter a are complex numbers. And they are known. So we have on each of these equations on the left side, we have a coefficient with the letter a multiplying one of the variables, and then we have a sum of such form. And each of these equations has an equal sign. And on the right side, there are other known numbers, b1, b2, b3, all of the numbers denoted here with the letter A and denoted with the letter B are numbers that are assumed to be complex. The variables, which are the unknowns, are also assumed to be members of the complex plane. And this is a very general formulation of a system of equations. There are m of these equations, and there are n variables. So here in this system of equations, there are m equations. And if we count the number of variables here, all these things with x1, and there are all these expressions with x2, and so on until we get to the very last part of each of those sums, right? And so here we would say there are there are n variables. So a solution is a set of values. In general, we're going to say the set of values S1, S2, S3, and Sn, such that when substituted for x1, x2, and x3, x4, all the way through xn, then every single equation of the system is satisfied. That is, the left side equals the right side on every equation. If a solution, the solution set in a linear system is a set which contains every solution to the system, and it happens that that solution set can be infinite. There could be systems with infinitely many solutions, and also there can be other systems that do not have a single solution. Okay, and if they don't have solutions, then this set called the solution set will be the empty set. This is an illustration that has three equations and four variables. So in this case, we have that n equals 4 and m equals 3, and the coefficients according to each number that is multiplying the variables here. So we look at the first equation. Here we have 1x1, 2x2, and 1x4. So that on the first row we have a11 is the first number, that's 1, a12, that would be this number multiplying x2, and a13 doesn't appear. So what happens to this first equation is that somewhere in here we have 0x3 plus 1x1. So the first equation really reads as 1x1 plus 2x2 plus 0x3 plus 1x4. Okay, so there is a coefficient here denoted as a sub 1, 3, which is equal to 0, and that term is omitted there. And then on the other side of the equal sign is 7, so here we would say that b1 equals 7. So we can see that the second equation has all the coefficients for all the variables, and so does the equation number 3. Well, turns out that the letter A, which in general is going to be denoted as A sub ij with two indices I and j. The index I denotes the row number, and the index j denotes the column number. We'll be more specific about that in just a few minutes. But let's see, we can represent or rewrite this system that has three equations, four unknowns. Okay, we're going to write that into a form that in which all the coefficients that are multiplying the variables are going to be stored in this rectangle. Okay, so for example, I'm going to take these numbers here. Um, these numbers here are going to form the first row, and the row is going to look like a horizontal list of numbers. So we have there 1, 2, 0, and 1. That goes for the first row. The second row is going to have 1, 1, 1, minus 1. And row number 3 here is going to have numbers 3, 1, 5, minus 7. Okay, and then the other set of numbers we have is these numbers that are stored in the letter B. They are on the right side of the equations here. So those numbers are 7, 3, and 1. And then the last thing that we store here are the actual variables, and these variables are x1, x2, x3, and x4. So these here, what I'm writing on in the bottom part of these nodes, is another representation of this set of equations. This is a set of linear equations. There are three equations for unknowns. We can write those equations by storing numbers into this rectangle, then this vertical thing, and then an equal sign and another vertical thing. So these things that are vertical are going to be called vectors, and this rectangle of numbers is going to be called a matrix. Okay. So I'm going to let you pause, read this information here, pause the video lecture for a couple of seconds, and then you can do this verification. Convince yourself means that you should take these values given here and go back to the equations and substitute those values into the equations and verify that each and every single one of those equations is satisfied. So we're going to say that two systems of linear equations are equivalent if their solution sets are equal. And then we're going to bring a definition of equation operations. The equation operations have to do with applying, you will see, relatively simple operations to each of the equations in the linear system. And so given a linear system of equations, following three operations will transform the system into a different one, and each operation is known as an equation operation. So what are these so-called equations operations? One of them is swapping locations of two equations in the list of equations. Another one is multiplying one of those equations by a non-zero quantity, and the next one is multiply each term of the equation by some non-zero quantity, add these terms to a second equation on both sides of the equal sign, leave the first equation in the same after this operation, but replace the second equation with the new one. Okay, so we can see this in action in one specific example. So if we apply one of the three equation operations to a system of linear equations, then the original system and the transform system are equivalent, meaning that the solution set is the same for both of these systems. That's why it is convenient to transform the original set of linear equations into another system that is more manageable. Okay, so what we do next is to discuss um, these to apply operations, equation operations to this system of linear equations.